Welcome in. I want to be able to do two examples with you, and the assumption will be that you have been exposed to vector and parametric equations of a line, at least in 2 dimensions. Now, I did a video on those 2 dimensions. I can put up a link up above there. I think it's useful to be able to watch that before you attempt these, unless you're already familiar with parametric or vector equations of a line. Now, the two examples that I have for you is, at least here is the first one. So construct a parametric equation of a line in 3 dimensions. So we are now in 3 dimensions. That goes through the point 2, 2, 0 and is perpendicular to the xy plane. Now, when you get into 3 dimensions, trying to do an equation of a line, we can no longer use y is equal to mx plus b. So that kind of static way of being able to do that doesn't really work. The standard equation of a line, the ax plus b y plus c is equal to 0, doesn't work either, because we are now in 3 dimensions, and you'll see later on, if you are going to use the standard form, you typically will find that you're going to be drawing out a plane. So how do we construct these lines? Well, one of them is indeed we can use a parametric equation, and another one is the vector equation. So I'll try to do actually both for this example so that you can see it. Now, let me just draw this out. And of course, doing 3-dimension drawings is rather difficult to be able to see, but I'll try to do the best I can here. So let's say I have my plane. All right, so within here, and this is my 3-dimensional sketch, and let's assume this is x, let's assume this is y, and this is z. And now if I wanted to do the point 2, 2, 0, and let's say this is going to be, let's say 1 and 2, and let's make this 1 and 2 right there. So what I would have is I would basically try to plot out this point. Okay, and it would be somewhere over here. So that's the point 2, 2, 0. So not the greatest of sketch, but that's what we would have. Now, it's telling us that we want to be able to have a line which is perpendicular to the xy plane. Well, if the xy plane, at least here it's kind of in the horizontal there that you can see it, then the line, okay, that would be perpendicular to this, that means it would have to be the line which is in the z-axis, right? So as you would be drawing this out, and then what this would look like is that you would have kind of this line going, okay, being parallel to the z-axis and then going through the point, and then of course it's going to also go down right there. And let me maybe this one put it in dots so that you can think that it's kind of going through that plane and then it's going down. So that's how our line would look like. Now, how are we going to construct our parametric equation? So from the 2-dimensional case, you may recall that mathematicians and scientists, they like to use this form, and this particular form would be that we would have, I'm going to just do the vector equation form in here. So r is going to represent the ray, which is going to represent our line, okay, in total. And then so what we need is we need one particular ray which touches the line, and of course the most convenient one will be actually going through that point. So we need this ray. This would be maybe called r0. So that particular ray right there is going to be the vector 2, 2, 0, and it just simply touches the line. Plus, now, because we're in 3 dimensions, notice we have the z component, and we're going to have a parameter, or parameter, t. So this particular t can be an element of the real number line, so that we can span out our entire line. Now, from 2 dimensions, you may recall that what we need is we need a vector. Now, in 2 dimensions, it was easy. It was basically a vector which was parallel to the actual line. So now the vector that's parallel here, I can obviously pick the vector, okay, which is going to be even the unit vector, okay, in the z dimension. So this could be 0, 0, and 1. So this one's actually very easy to do. And if I'm going to now take over and let t be anything, now of course if it's 0, then it's going to be just the point 220. If it's going to be positive, it's going to be every single point going up. And then if the t is negative, it's going to start to go and traverse the actual line through every single thing coming down. So that is pretty neat to be able to do that. So my r vector, I'm going to actually try to draw it out for you. So what it will be, okay, is, you know, the addition of these, and it would be any kind of point on the line. So if t is positive, now if t is 0, then it's going to be this right here. If t is positive, then it's going to be kind of going up this line all the way through, and the bigger the t is, you know, the further and further away, and we're trying to find the point on that line. Now, when t is negative, well, then we're going to go and start to go down. So this is going to be now subtracting that vector, so it's going to start to go down in that direction, and it's going to now traverse that particular line all the way through. Now, this would be a vector equation of the line. So this one right here, and this is in 3 dimensions. So this is the vector equation of a line in 3D. Now, if we want the parametric equation, so the parameters, right, as we're going through, then that is actually very simple to do. So let's call this line L, and what we're going to do now is, in 2 dimensions we had 2 components. We had a component for the x values, we had a component for the y values, but now since we're in 3 dimensions, we're also going to have a component for the z values, okay, or the z values, depending how you pronounce it and where you are watching this particular video from which country. So how we would do this is we just simply take our x components, okay, so within here, so this x component is actually pretty simple because it's going to be just 2 plus my t times 0. But what is t times 0? It's just 0. So this is going to be always equal to 2. And then my y component, okay, so notice it's going to be the same thing. It's going to be just 2 right here plus the t times 0, which is again going to be just 2. So that makes sense because we are in and we're actually parallel to the z-axis. And then as you're going through, your last component would be just 0 plus, you know, the t times 1, which is just going to be t, which I guess is going to be just simply t. So what is really neat, in the parametric form, we have just 2, 2, and then a t. So it's a very nice and simple representation. And it would give us exactly this line if we allowed, you know, t to be equal to any element of the real number line. So that's what we would have for this example. And this is your parametric equation. So that's really nice. Now this one we can still visualize. Now if the lines are actually not that nice and they're kind of, you know, scattered along, then it's very difficult to actually draw this and be able to visualize these particular lines. So here's another example that I have for you. So this one gives you 2 points. So construct a vector equation of a line that goes through the 2 points. And now here they are. So those are my 2 particular points. So if you take these 2 points, you can certainly construct the vector equation of the line. It is indeed in 3 dimensions. Because from any 2 points, we know that the line, you know, once you attach the line and extend the line through, it will indeed be a line, except it's in 3D. We don't really have any slopes or anything, but we can certainly find an actual vector which is perpendicular, which is parallel to these particular points. So how do we do that? So let's kind of start from the beginning. So we have our r, so this is in vector equation form, so we need some initial starting point, plus we need a t, and then in 2 dimensions, you know, mathematicians sometimes, depending again on the textbooks, might use an m, which is the vector, which is simply the vector which is parallel to, in this case, the actual line itself. So that t, as we saw in our first example, is going to be spanning out through our real number line. Now, this particular vector doesn't matter what it is. You can take any of these 2 points, or any point, in fact, on the line, and then construct a vector out of it. Now, I'll just take the first point, which is going to be 2, 1, and -5, and that's going to be the vector which is going to be going in. So that means, of course, it touches that particular point. Now, we need plus our t. Now, in order to construct our m right here, well, this is nothing else but simply now transform the actual, so, let's call this point P1, let's call this point P2. Those are my actual points. And the vectors which are attaching to those points, so it's like, P2, which is the point, but I'm going to put a vector on it, I can subtract the 2 vectors, and of course it's going to give me the vector which is parallel. That's what you saw in the 2-dimensional video as well. So when you're doing this, it's actually not that hard, because you can just take these, construct them into vectors, and then subtract them, and then you will find exactly what this parallel vector is. So this is going to be 3 minus 2, which is 1, -2 minus 1, which is -3, and then 1 minus -5, which I guess is going to be 6 in this case, because the negative and the negative is going to give us a positive. So if I bring this back in here, this is actually the vector equation of my line right there. So that is it. Now, this is very difficult to try to visualize for us in 3 dimensions. In 2 dimensions, it was actually a lot easier, because we can go back to the y is equal to mx, and because you have worked with y is equal to mx plus b form for so long, so for some people actually all the way from elementary school, and for others maybe from high school onwards, right, as you're going through all the way to grade 12, then it's easy to visualize 2D. 3D, maybe it's easy to visualize this one, as I kind of drew it out in your mind, but this one would be very difficult, even just picturing out where those 2 points are. If you're really good in terms of visualizations in your mind, if someone gives you a point, you can maybe even close your eyes and think about it, but it's hard to do that. Now, I'm going to just try to do it. I'm going to use math3d.org to try to graph this out. I'll put the points on. And then, so we'll connect the points together. Then we'll try to see, I'll put the vector, so the vector R0, and then we'll try to put the vector M, okay, so that you can see that, those would be the vectors. But again, in terms of traversing it all the way through, that would be difficult, okay, to be able to do that. So let me just graph these, and then you can visualize it with me. So I'll be right back. Here are the 2 points. I just decided to just plot the 2 points first. So notice 3 dimensions, they're kind of, floating around in there. That's what we would have right there. Now I'm going to add a line, right? So this is going to be the line that actually goes through those 2 points. So in math3d.org. So thank you guys for doing this so that I can plot these out. Now I can put these points in here. So this is going to be from point 2, 1, -5. I'm going to put the other one as well. This is going to be 3, -2, and 1. Notice that the way that the line is drawn, at least in this particular software on the web, is that it connects the 2 points directly. So now that's pretty cool, because we can kind of, see it, floating above there, right? And then we can kind of skim around and be able to see that as a line. Now, of course, this line actually extends, to infinity, both up and down. And now if you wanted to graph the actual, vector, so here's I can graph a vector. So let me graph the first vector, which actually touches the line, which is our starting point. So this is drawn or given exactly like a point. So now they use here the brackets, the square brackets for everything, which kind of throws us off a little bit, but right above it, it just defines a point, line, vector. So notice right here, I've just drawn the vector, which really touches that particular point. And now I can draw my other vector, which is going to be the vector which is actually parallel to the line, which is the one that we found, which was 1, -3, and 6. Okay, so notice, and here you can actually very nicely see that it is indeed parallel. So now it would be the addition of those two vectors. And as you're adding those two vectors in, you can find yourself finding, any value, for example, on the actual line, and it would traverse it all the way through. Now, in this one, I can't actually program it in. I'm actually not sure if you can do it on Math 3D. So in Desmos, I like to do, the programming of traversing a line. You would see that in that previous video on 2D. You can go back to the beginning of this one and then click on that link to watch it. But in here, you do see that indeed it's kind of a visualization more so in 3 dimensions. And even in this, it's still kind of difficult to be able to see this, right? You have that line, and now you have the two vectors. Of course, you have to add them together, and then you have your t, which is a parameter, which now is going to scan that line all the way up and down. So if it goes down, right, so it would be for negative values, and then if it goes up, it's going to be for positive values, okay, above that point. All right, so that is how you can do this, how you can visualize it. So I leave it up to you if you want to go on math3d.org to play around with these tools. I think it's great. If you're a teacher, you can certainly use it and show your students. But those are the two examples I wanted to cover. I think with the 2D and now these two examples with 3D, you should have a decent understanding of how to actually come about the vector equations and the parametric equations for a line. All right, so thanks for watching. We'll see you hopefully in a future video. Bye, everybody. Cheers.